a triple threat here from the OpenElectronicsLab. Three presenters, and they're going to give us an overview of their development of open hardware and kind of transitioning from getting into that into some really awesome hardware that they have developed and that are available for people to look at, fork and reuse. So please give a warm welcome to the OpenElectronicsLab.
Thank you. So I'm Eric. With me is Kendrick Shaw and Ace Medlock. We're the repository admins of the OpenElectronicsLab. And when we got started in 2011, we were a lot more novice than we are today. Perhaps like some of you, back in 2011, I had never done SMD solder work ever, never done any surface mount. I looked at the multi-layer boards and I felt really pretty like that end of stuff was outside of the realm of hobbyists. I do a little bit of through-hole soldering, that's kind of it. But then there was this really interesting chip that came out. It was only available in an SMD package, and we thought, well, okay, maybe we can build a breakout board for it. So a single, a single thing we can do for that. And sure enough, we were able to do that. I only screwed up one board in the process, so it wasn't too bad. And from there, we went all in on the surface mount, and we built something that we weren't just getting EEG signals on, but we were able to get ocular signal and EKG and muscular things. And we were even able to control a mouse pointer using our mind. It was pretty neat. And people started asking, hey, can I get one of those? But these things were big, they were difficult to build. We didn't know enough about putting test points on to modularize your design to make it easy to debug. And so we said, no, we don't want to be in the we don't want to be in the business of testing this stuff. So so we designed something that was a little bit more accessible. So something that you can build yourself, or you can have somebody fab it for you. It's pretty straightforward. It's not super expensive. Sits right on top of an Arduino, and you can play with driving your quadcopter or whatever. And that got people interested. And one day, Robin from Hementon joined our session, and he gave us the insight that in the low resource environments of poor countries in Africa and such, what's killing their devices is not what I expected. I expected like humidity and dust and things like that. He said it was bad power. And so we started thinking, well, maybe we could build a device suitable for that environment. So how do you get from we're novices to we're going to build a piece of medical equipment? Well, there's a lot of FOSS tools out there to support you from the novice through your growth and your experience. And I think the Arduino boards are a great place to start, and there's all sorts of tools to get you going. KiCad is what we started with, and as we've grown, everything we've even wanted throughout KiCad, it's handled for us. We do some fairly complex schematic design, obviously, and then here's like a 6-layer board. And by the way, if you're doing any schematic design, or excuse me, board design today, I really recommend using 4-layer boards, because anytime I'm trying to go diagonal across the board, I don't want to try to snake around all the components. I want one layer that's just horizontal, one layer that's just vertical. I via down, go over and up, pop out, and then I'm there. Really saves time on my layouts. And then also, I recommend doing some yourself, hand do some yourself, but it's not that much expensive to get them pre-populated, and you can get them with combinations of through-hole and SMD, two-sided. This thing has everything except one component, and that way, I have to do the Vroom chip ourselves, but that's not a huge time investment. The Arduino build environment, no matter how novice you are, you say, I'm not a C coder, or I don't do embedded dev, this is a great place to start. If you've done any development whatsoever, they've really made it fairly easy. Now, as you get more experience, you may move away from this tool, you may use more, you may like your different libraries and such, but in terms of early prototyping, to this day, we still reach to this first when we're playing with something new, because it's so quick and easy to get up and running, get something going. And then another tool that we really have enjoyed using is OpenSCAD. I'm not an artist. I'm not going to draw beautiful things in the whatever the art programs are. But I am a developer, so I want to be able to programmatically describe this is the shape of the thing and have it render, and then have one of our other collaborators print it out for us. So so that's a little bit about how the tools are, and I'll hand the mic over to Ace, and she can talk about soldering. Thanks.
So as Eric mentioned, when we started out, we were really pretty intimidated by doing surface mount soldering. And so we designed a board that had only one chip on it that had needed surface mount soldering. And we got on YouTube and we took a look at some videos and saw how other people were doing it. And that actually made us pretty bold. It worked, as Eric said, second try, which is not too bad. And so our next board, we decided we wanted to reduce the noise, which meant that using all surface mount components. Now, surface mount components are pretty tiny. So the way we decided to approach it is by using solder paste. So solder paste is kind of sticky stuff. You put it on the pads, you stick your component down to the pad, you heat it up with a hot air gun, and then the component's soldered on. So that all seems pretty straightforward. But when we tried it, we discovered we had a lot of bad solder joints. It didn't actually work that well for us. Now, my background is in medicine, and when I have to diagnose a problem, I like to get a good look at it. So I stuck it under the microscope, and what I found was this. So when you look at solder paste under the scope, it's made of these tiny little beads. So these are little solder beads stuck together by the paste. And when you heat it up, you get something like this. But you can also see it melt, but still get something that looks like this. Now, does this conduct electricity? I don't know. But in some cases, it appears it doesn't. And so for me, that didn't work real well. So the way I do it nowadays is I do it under the microscope. I do it under a dissecting scope. So I just put the board under the scope, heat up the soldering iron, and when you do that, it looks about like this. Now, the trick is to get a little bead of solder on the end of your iron, because the iron itself is too big to make a good connection between the pad and the component. But the little solder bead, the solder is a great conductor of heat. So you can stick that right on there, heat it up, get your solder. Then you just pull the iron away and do the other side. And then you're all done. Now, you do get some pretty ugly looking solder joints sometimes, but that's okay, because the job of a solder joint is to conduct electricity, not to look beautiful. So you'll make some modern art, and that's all right. You can do some really tiny parts this way. This is a 0201 capacitor that's hand soldered. This is the same magnification as the solder paste that we saw earlier. And the nice thing about that is that you learn to be bold about being able to fix your mistakes. So this looks great, looks beautiful. I didn't solder it. But the problem is that the pads are in the order GGS and the feet are in the order of GSD. So that's not so great, but that's no problem. You just heat it up with your hot air gun, pick it up, turn it around, stick it back down, and it works just fine. And so, but what about if you forget a component? Well, you're designing, so you forget to put something on. Well, that's not a problem either. You can just do some green wire fixes, and those through-hole components make for great green wire fixes. What if you accidentally put a trace somewhere where it doesn't belong? Well, you can fix that too. You get out your X-Acto knife and cut through it. You can even, if you have both problems, you can even lift up one of these little feet and hook a green wire onto the little foot, but sometimes you're going to break off your little foot when you do that. And if that happens, you can just Dremel into the chip and stick on a green wire. So you don't really have to worry about that either. You'll make mistakes, you will, but you can fix them. But it's also good to anticipate errors, and that's what Kendrick's going to talk to you about.
So much like testing, a little time spent thinking about safety can save you and others a lot of pain in the future. So we're going to talk a little bit about that. So the first step when you're thinking about safety is basically just take a moment to think about what could possibly go wrong. And if you have any real imagination, you'll come up with a very long list of things that could go wrong. From there, next ask yourself for each of them, how serious are they? A lot of them might be pretty minor. Some of them might be life-threatening, especially if you're building medical electronics. Then finally next ask yourself how likely it is. And again, this can vary dramatically. You don't have to solve every problem that's out there if it's unlikely to happen. Your device, if dropped from an airplane, might seriously injure or kill someone. You might not need to spend a lot of time worrying about it. So then once you have that amount of harm and likelihood of harm, then from there you can calculate out a risk or approximate a risk. There are formal design methodologies you can go through this, but the main idea is you just combine the two and come up with in your mind, is this an acceptable level of risk? And what's acceptable can vary quite a bit. Somebody going out there free climbing is taking on a lot of risk, and they know they're taking on a lot of risk, and they're doing it because it's fun. You can do the same thing in your hardware design as long as you're aware of what the risk is and you've chosen to assume it. And same thing with in a medical environment, for example, a defibrillator is a device designed to stop someone's heart at the press of a button. This is inherently a dangerous device because if you do that at the wrong time, it can be life-threatening. But it's worth the risk because if you do it at the right time, it can save someone's life. If the risk isn't acceptable, then you start thinking about mitigations. And basically, you can reduce the likelihood of the event or reduce the severity of the event. So for example, if you have a pacemaker that you're worried about someone hacking into, you could always remove the internet connectivity from the pacemaker if you don't really need it and make it a lot safer, taking away functionality in the process. Or you can decrease the severity. So for example, if you have a life-saving device and it can fail in a catastrophic way, making it fail loudly rather than quietly is something that's more likely to attract attention and bring people in to fix it. So for a lot of our devices and typically for medical devices, one of the common things we worry about is electrical shock. You may think, oh, you're dealing with 5 volts, no big deal. We touch 5-volt circuits all the time, don't feel anything. Important thing there is that's with dry skin. Here we're attaching electrodes, and it turns out that it's current that matters more than voltage for the risk of these things. So for example, a pacemaker typically runs at about 1 to 2 volts for triggering heartbeats. So these aren't very high voltages. And they're relatively low current where it's kind of tens of milliamps to the skin, tens to low hundreds, and literally tens of microamps to the heart. And if you have an IV in or things like that, then you can end up with very low currents, very low resistances. These can show up in the obvious way as far as flowing in one electrode in your device through the heart and back out to the other electrode, but it can also be something a little less obvious, like maybe through an electrode in your device, through your heart, to something like a water faucet that you're touching. Or even less obvious than that, maybe you're hooked up to another device that's malfunctioning, and if your device will connect through you to ground, your device can contribute to a shock. And although your next of kin might blame that malfunctioning device, you'd rather be around to blame the device yourself. There are a lot of things you can do to mitigate this. So you can simply, and you'll notice those last 2 cases, you're connected through the ground, which means both devices are plugged into the wall. You can unplug from the wall, run your device off a battery, or use isolators. Nowadays, you can cheaply buy isolation that will, power isolators and data isolators as far as optocouplers. If you do that, you want to make sure there's gaps, which we talk about as clearance, between the isolated parts and gaps across the surface board and off the surfaces, because surfaces can get moist or dirty, and so that distance is usually larger. There are a lot of standards, but 8 millimeters is usually a pretty good rule of thumb, and it's on the safer side. We'll skim over this because we're running out of time, but the important thing is there are standards for how much current your device can run through a person. They are very low numbers, and you have to think about not only what can it run through when it's working properly, but what happens when things start breaking. Which is another area to think about. So if your amplifier, the chip that you have as your amplifier shorts out and that high impedance connection to the patient now suddenly connects the patient to voltage and ground, what do you have protecting the patient? And for an example like that, typically you can just put in some resistors in the leads leading off to the patient to make sure that total current flowing through in that failure case will be less than the safe amount of current. So with that, just wanted to close. Basically, spend a little time thinking about safety. It's not hard and can go a long way. You have a lot of great tools for getting into electronics and open source hardware. Don't be intimidated. Just get your feet wet, jump in, and you'll get better as you go. And happy hacking. And we have a number of references up here for you.
So, any questions for our group here?
Well, I don't want to ask a question. I just want to say that so far this is the best presentation I've seen in FOSDEM.
We're glad you enjoyed it.
Thank you.
I reacted so strangely when I saw the first soldering things and the scratches on the SMDs. I really have to congratulate you for your creativity. And at the same time, I totally understand all the thing about that, because some project needs to be done or to have a very early test, and this day can be probably a Sunday, so you can get a new SMT or better stuff to evidence in the project.
We typically work on Saturdays. Not a great day.
get, or where do I get a dissecting scope from?
Sure. Yeah. So the question is, where do you get a dissecting scope? And the answer is, of course, the internet. So this is not really a special dissecting scope. This is actually just the cheapest one that had an arm, because a lot of the scopes have a platform where you're supposed to set your specimen, and you will burn that platform. So don't get that one. Get the one with an arm that comes out, and you can set your board on something that's heat resistant.
How much did you pay for that?
It was about 300 euros, I think, to 250, 300. So.
Cool, thank you. Yeah, in the back.
Well, just suggesting you have like a USB microphone for like $7.
Yeah.
So,
Yeah.
question?
So Kendrick actually uses one of those. I prefer the analog version.
Very special one. What was your rationale to have that good galvanic isolation?
So that's actually the.
Here, speak in the mic and repeat the question.
So he's showing us a version of our board, which is great to see. And the fact, I believe you're pointing to the two DC to DC converters on the bottom for our galvanic.
And the isolation buffers. I mean, you have this very, very clear interruption of everything, of all power planes in the between the ADS and the Arduino.
Yes, that is an excellent question. This gets down to the idea that, especially if you're doing an ECG, someone may attach a defibrillator to the patient and put 5,000 volts or more through the patient. You don't want that getting to the person at the computer or other operators. So you want to have good isolation between the patient side and the side that the computers are on. So that gap there is making sure that we have that 8 millimeters of distance between any metal part on the board on the isolated and non-isolated side.
And there's two of them, which reinforces.
Yes, so we want to make sure that any component can fail. The data isolation, we have a single one because it's rated for reinforced isolation, so it's rated to be as reliable as two pieces of equipment normally. Then we have two, on the other side, we have two power isolators, such that if one of them fails, the other one is still providing that 5,000 volts of isolation. Okay.
Follow-up question?
Yes.
Are you pacing nowadays?
We are not pacing at the moment. We may add that to our list. We've talked about it.
Yeah.
But.
Lots of more follow-up questions offline.
Okay,
great.
Another question.
Did the Dremel chip survive the operation?
Yes. The question was, did the Dremel chip survive the operation? And yes, the Dremel chip did survive the operation. And just to be clear, this is where the wire would go into the plastic case before it goes down to where it's wire bonded to the chip. So it's not soldering directly to the chip, but it's soldering to the lead going inside the plastic case.
Well done.
Thanks.
Any additional questions? Okay, thank you so much.
Thank you.